First moment. That's the most important concept in physical therapy, of course. Moment concept. Here is the block again. Here the force again. We assume that the axis is here. Yeah. What's the result of this force?
Rotation.
Rotation. Rotation. In what direction?
Clockwise.
To the right, clockwise. Why?
Because it's coming.
Why?
From
A
the
rotation
left.
clockwise?
It's coming from the left and it's up.
What?
It's coming from the left and it's like on the top corner.
Yeah. Okay. It's coming from here and it has a lever arm.
Oh, yeah.
It has a lever arm. What is the lever arm? The lever arm is the shortest distance from the action line of the force to the axis. So this is force 1, and this is force 2. This is force 2. With this action line here. What's the difference between both? The smaller lever arm. The forces are equal, the lever arm is smaller, this lever arm is smaller. So we call this lever arm here D1, and this lever arm D2. What's the result of the short lever arm?
Slower acceleration.
Small moment.
Small moment. That's the only correct answer. And what is moment?
The result of the force in the lever arm.
Yeah, and what was the relation between moment and result and force and lever arm? What's the relation between moment in one hand and force and lever arm in the other hand? What the mathematical relation?
I mean, the bigger the lever arm, the bigger the moment.
Okay, the moment is the product of force and lever arm. The moment is the product of force and lever arm. The moment is the product of force and lever arm. So the bigger the force, the bigger the moment. The bigger the lever arm, the bigger the moment. That's correct. Right? So the forces are equal, but moment 1 is twice moment 2. Why? Because the lever arm is twice. What is the result of this moment? Think about force. What is the result of this moment? Rotation to the right. Yeah. But what could you say about the movement, or rotation to the right? Could you more specify this? Think about force. Force, what is the result of a force? Acceleration. What is the result of a moment?
Rotation.
Acceleration
Acceleration.
as well. Acceleration as well. So what is the acceleration? Acceleration to the right. Rotational acceleration to the right. How do we call this? Alpha. How do we call this alpha? So the moment has as result alpha. Force is mass times A. Force is mass times acceleration. Hey? This you understand, eh? The more mass, the slower the acceleration. So the mass determines the measure of inertia. Inertia. And here,
Distance times.
the moment is smaller or bigger. The smaller or bigger, being smaller or bigger of the moment, depends on force and lever arm. Then we have a certain moment. The moment has as a result alpha. So yeah, there must be something like mass. Yeah, and this mass, this resistance against inertia in rotational sense, we call it the moment of inertia. Moment of inertia. I. And this I would like to explain. This is very important to understand in movement analysis, what I is. So translation we have F is m times alpha, times A. In rotation we have m is I times alpha. Dus 100 years after Newton, this is discovered. Totally parallel Translation and rotational laws are the same, principally. Yeah.
But then can I be expressed as the mass times the lever arm?
Of the mass.
Yeah, of the mass.
Of the mass.
The
That's
lever
correct.
arm.
The average lever arm of the mass in relation to the axis times the mass is I. So it's rather abstract. I will explain.
Yeah, but if you substitute.
And this we call a moment of inertia. This is also mass of inertia, and this is moment of inertia. We call it mass. I will try to explain. Yeah? This is the most important item in movement analysis to understand the I. I hope you will understand. For you. I try to explain. There are several experiments. When I had your age and I was student at the Faculty of Movement Analysis, my professor asked me, because he had only one student, that was I. My professor, yeah, I was the first one. First student at Faculty of Movement Sciences. First student. And my professor sent me everywhere. There was no faculty. So I had to go to psychology, I had to go to that. And I also had to go to the Technical University in Leiden, in Delft. And he asked me, determine the moments of inertia of the body parts. Or I thought, I do it in an afternoon, but I determined after half a year I had some moments of inertia, forearm and the lower leg, something like that. It was very difficult, more difficult than we expected. So every body part has a moment of inertia, like every body part has a mass. A translational mass, a rotational moment of inertia. Here is a block. Here the same block. And we have to understand that we work in a horizontal plane. So here, this is the experiment. This is a bar. And this block here is connected like this. Something like this. Horizontal. Horizontal. So we watch from above down. Yeah.
Top down.
Top down. We watch top down. Do you understand it? So the movement here is an axis, and here is an axis. Here's an axis. You see? Horizontal in a horizontal plane. I have a force. This is force. F1. And this is force F2. This is force F2. So the force has as a result that it starts to topple. The force has as a result that it starts to topple. The masses are 10 kilograms, are equal of both. The masses are equal. Yeah. This force has a lever arm, as you see. And this force has a lever arm, as you see. So you see force times lever arm of 1 and force times lever arm of 2 are equal. So moment 1 is moment 2. The moments are equal. The object starts to topple. The object starts to topple. Which object gets a bigger acceleration?
Second.
2. A bigger acceleration. So you expect that this has a bigger acceleration. So moment is times acceleration. Moment is times acceleration. You expect that this acceleration is bigger than this acceleration. It's not true. It's not true. Why not? Because this has a certain mass, 10 kilograms. This has a certain mass, 10 kilograms. The same mass. But you see, now you get your remark, yeah? But you see that the distribution of this mass in average is near the axis. And the distribution of this mass here is far from the axis on average. So what you do theoretically, you count every distance of every molecule to the axis. You add them and you divide them by the amount of molecules. Theoretically. Then you have the average distance of the molecules to the axis. And the average this is average, the average distance of this one is big. And the average distance of this one is small. So the moment of inertia of this one here is small. And the moment of inertia of this one is big. The big moment of inertia. So because the moment of inertia is big, acceleration is small. The moment of inertia is small, acceleration is big. So the nearer the mass to the axis, the bigger the acceleration. The more far away the mass to the axis, the smaller the acceleration. I will give some examples, yeah?
Same as you're saying that the nearer the particles to the axis, you're relating that to acceleration. Is it also right to say that the further the particles from the axis, the bigger the inertia? Can you also relate it immediately to the inertia?
The further the particles from the axis, the bigger the resistance to movement, the moment of inertia. I will give you an example. Yeah.
Smaller the resistance.
But Bert, in this specific example, then you only take into account the two forces that you group and not, for example, gravitational force.
Yeah, that's why I put it horizontal. You see, in the rotational direction, there is no other force.
Of course,
Yeah?
we're working top down.
This is why I put it horizontal. That's for that reason. So you don't have application of the gravitational force. Very simple examples. Here is let's say a woman, not a man, but a woman. Here is an arm. Here is an arm. And here is the same arm, you see? Here is the same arm. Yeah? Here is the same arm. Here is a muscle. The delta ED is posterior of the pectoralis major, doesn't matter. And here is a muscle. The same muscle. The muscle contracts with a certain force. Give it a name. 10 newtons. This muscle contracts with the same force. 10 newtons. 10 newtons. Here is a distance, d. Here is a distance, d. Distances are equal. Forces are equal. Moments are equal. So at both sides, the horizontal adducting moment of both forces are equal. Question now is, I see acceleration in this direction, I see acceleration in this direction. Which acceleration is biggest?
One on the left.
Left. Why?
Because the mass is closer to the axis.
Because the mass is closer to the axis. So, moment is I times alpha. Moment is I times alpha. Moments are equal. I is not equal. Because both arms weigh 10 kilograms. But this moment of inertia, the center of moment of inertia is about here. And this center of moment of inertia is about here. It's closer. So the average distance of the mass to the axis is far away. The average distance of the mass to the axis is nearby. So this is a small I, this is a big I, so this is big acceleration, and this is small acceleration. And we use so much this principle because the faster you run, the faster you have to flex your hip joint. It's not possible with an extended knee. You must flex the knee as much as possible to decrease your moment of inertia. You flex so much the knee joint to decrease in the moment of inertia so that you have, with the same moment of the iliac psoas, a bigger velocity. That's the story. That's the story, huh? So you make the moment, movement is playing a game with moment of inertia. You make smaller, you make bigger, smaller and bigger. And you see it in the pirouette, huh? The pirouette, and it's close and wide. Close and wide. Close, moment is another principle, it's an impulse moment principle, but it looks like this. Huh? You make the moment of inertia smaller, fast, Moment of inertia. Bigger, slow. We understand this? So this principle is used often.
So, what's the units then? Inertia. It's
Moment of inertia.
Inertia. It has the acceleration is meter per second square. Moment is
Translational acceleration is meter per second square. Rotational acceleration is radials per second square, and you can transfer them to degrees. Degrees per second square. How many degrees per second square you travel in the joint? But we don't calculate. We don't calculate. I hope you to understand this principle here. Next week I start with impulse and impulse moment and so on. Yeah? You take the time. How long lasts this class? I don't know. Okay, half an hour on then I can continue. Oh, then I continue. I'm sorry. Then I continue. I thought that it was over. Then I continue. Do you have questions till now? Here you see this story, yeah? Hey, here you see this story, what I told you just now. Yeah? So this is moment of inertia. I go back to moment. To the principle of the moment. A force, the axis, and the force. What's the result of these forces?
Rotation, clockwise.
Rotation clockwise, eh?
Mm-hmm.
This is F1, and this is F2. You can add them, eh? You can add them. So moment 1 is rotational clockwise. Moment 2 is rotational clockwise. So you can add them. The entire moment is m1 plus m2. What is the acceleration actually then of this this object? Is I times alpha. Is I times alpha. Yeah? So this alpha here depends on the magnitude of the moment and on the magnitude of I. How it is subdivided, how the mass is subdivided around the axis. This here. What the F1 and F2 are equal. The action line is equal here. What the consequence?
No movement.